In this lecture, we will study about the independent set of graphs. Before formally defining what is an independent set, we will first see where this independent sets can be used. The first problem where it is most commonly used is the storage problems. What is meant by a storage problem? There are chemicals in a bottle. Of course, it could react and create damage. So, the problem is to store the chemicals which do not react with each other. And of course, this has to be placed in minimum number of rooms. So, this will be the storage problem. Suppose I have chemical 1, chemical 2, chemical 3 and chemical 4. I can keep all the chemicals in a separate room, thereby occupying these 4 chemicals in 4 different rooms. But what is required is it has to be placed in the minimum number of rooms. Suppose if chemical 1 and chemical 3 do not react with each other, then in that case I can place chemical 1 and chemical 3 in a single room and then place 2 and 4 in a single room if they don't react, and if they react I can place chemical 2 in one room and chemical 4 in one room, thereby I can reduce the number of rooms from 4 to 3 or less than 4. So, that this type of problems can be solved using the coloring technique. So, now what I do is I assign same color to chemical 1 and chemical 3 and different colors to C2 and C4 other than the one that has been painted for C1 and C3. So, when I do it, the bottles with same color can be placed in a single room, and thereby you can have the minimum number of rooms to get the required solution to the storage problems. So, the coloring principle can be applied here, and similarly you have a problem called as the timetable problems, timetabling problems. What does this timetable problem say? I have, say for example, I have 4 teachers, T1, T2, T3 and T4 as an example here. And I have 6 classes, C1, C2, C3, C4, C5, C6. And I have only 4 rooms. Okay. So I have to assign the teachers to the classes, okay, one at a time. And out of these 4 rooms, okay, there is a condition that I can use all the 4 rooms or 2 rooms or 3 rooms as the case may be. So I have to frame a timetable satisfying, frame a timetable satisfying number 1 teachers workload, number 2 room constraints, constraints of the students if any. Okay. So in this case, still you can use the coloring principle to frame the timetable here. So in this case, the concept of coloring can be applied to vertices of a graph or edges of a graph. It can be applied to a vertices of a graph or edges of a graph. Okay. So the vertex coloring is the coloring concepts on the vertices and the edge coloring is the coloring concepts on the edges. You have another coloring called as total coloring, coloring concepts on both the vertices and edges, vertices and edges. Okay. And of course, in the coloring of vertices, you have 2 types of coloring. One is called as the proper coloring, other one is called as the improper coloring. What is meant by a proper coloring? Adjacent vertices are given different colors, and the improper coloring is adjacent vertices are given same color. So these are various types of coloring. Now we will be using the basic coloring concepts. So I will define what is a vertex color, vertex coloring. Coloring the vertices of the graph in such a way that adjacent vertices receive different colors. So, in this case the adjacent vertices receive the different colors, and the minimum number of coloring is called chromatic number of G. So, if you look at this particular example here, A, B, C, D and E. Okay. I can give different colors here, A, B, C, D and E. Okay. The colors that I have to use here is, suppose if I give A with C1, B and E has to be given with different colors other than C1, and since B and E are adjacent, I have to give C2 and C3 to B and E. Okay. With respect to C and D, I can give C1 and C2. So, I have a partition of the vertex set, namely AC will be in one group, B and D is in another group, and this E is in the third group. Now, if you note, the coloring was done in such a way that adjacent colors receive different colors. If we have vertices of the same color, say A and C are having same color, but they are not adjacent. In fact, the coloring concept is only because of this. Okay. They are not adjacent. So, this leads to the concept of independent sets. Okay. Now, what is an independent set? A subset S of V is an independent set if the subgraph induced by S contains or is an isolated graph, or in other words, any two vertices in S are non-adjacent. Any two vertices in S are non-adjacent. They don't have an edge between them. And now, the maximum cardinality of an independent set is called the independence number of G and is denoted by alpha of G, denoted by alpha of G. Okay. Now, the maximum cardinality has to be checked in case of an independent set. While discussing about the dominating set, we had defined what is a minimal dominating set. That is, a proper subset of a dominating set is not a dominating set. Similarly, we have maximal independent set. A maximal independent set, okay, is defined as an independent set S which is not contained as a proper subset of any independent set. And of course, here you have this as a note. Every maximum independent set is a maximal set, converse need not be true, So, this is the definition of the independent set. So, you pick up the elements which are not adjacent, and that you call it as an independent set. And the cardinality of a largest independent set is called as the independence number, and it is denoted by alpha of G. Now, we will be using this maximal independent set. What is meant by a maximal independent set? An independent set which is not properly contained in any other independent set. Or if you have an independent set S, and if you do not have an element in U in V minus S such that S union U is an independent set, then that is called as a maximal independent set. Our aim in this lecture is to enumerate all the maximal independent sets. So, that is the main aim of this particular lecture. So, after giving all these definitions, we will give an example and find out the independent set for this graph. So, as an example here, you consider the graph, I will have a smaller graph like this. I have taken a smaller graph. Okay, I will name them A, B, C, D, E, F, G, H, I, G. Okay. So, if I take independent sets, say S1, okay. Suppose if I select B, then I cannot select the neighbors of B in the set. So, I cannot select H, A, E and C. So, I can select any one, either J or I. Suppose if I take I can also take D and I can also take F. So, this will be one independent set. This is one independent set. Suppose if I take another set like this, J, C, A, and then G. So this will be another independent set. Okay. So if I take a proper subset of S1 and S2, that will also be independent. So now I have to check whether can I get a independent set whose cardinality is greater than 4 for this graph. Okay. Anyhow it will be 4 because in the middle part of the graph I can have a maximum of 2 independent elements, AC or AD, okay, or BD or EC. And similarly in the triangle IJH I can have only 1, and similarly in K2, F and G I can have 1. So maximum I think it will be 4. So this will be a independent set, and alpha of G for this graph is always 4. Okay. So this finding out the independent set for this smaller graph, this seems to be easy, but the overall, if the graph structure becomes larger and larger, then finding out the independent set or independent number is going to be difficult. So as I told you, we will be using the Boolean algebra or Boolean arithmetic to enumerate all the independent set for the graph. Before proceeding with the enumeration problem, we will try to characterize the independent sets using the concept called as covering of G, covering of graph G. Okay. As I told you, finding out the independence number is difficult. So when I find the complement of an independent set, namely the covering of a graph, then in that case either solving an independent set or solving a covering number of a graph will be same. So first we will find the relationship between independence number or independent set and the covering set. Before moving into the process of finding the relationship between them, let me define the covering number of a graph. Okay, what is meant by covering number of a graph? A subset S of V is a covering set if every edge in G has at least one endpoint, in S. The minimum cardinality of a covering set of a graph G, denoted by beta of G, is called the covering number of G. Is called the covering number of G. So in this case, what could be the relationship between alpha and G and beta of G? So that is the process that we have to do. Before moving into the process of finding the relations. Okay. Now what I will do is I will find the covering number for this graph. Okay. So what will be the covering set? Suppose if I take S1, okay, I will have B. Suppose if I take B, that would cover 5 edges, 1, 2, 3, 4, 5, BA, BC, BH, BI and BE. So I have to take H. When I take H, that would cover HI, okay, and necessarily I have to take F because that would cover FG. If I take F, cover vertex F, that would cover FG and FE. So to cover the edge EG, I have to take either E or G. Suppose if I take G, okay, if I take G, then if I take E, automatically that would cover EA, okay, EB, ED. So now I have to cover only the edge CD. I have to take any one. So I will have C. So in this case, I have B, H, F, C, E and C as one covering set. Okay. Now let me find another covering set which could be smaller than this 1, 2, 3, 4, 5. Okay, I have to take a smaller one. Okay. I think this would be the smaller one. Let us see. If I take B, E, then that would cover these edges. So in order to cover these two, HI and FJ, I have to take 2. So 2 plus 2 will give you 4 plus 1, 5. And only I have 5. Okay. So I think I require minimum of 5 vertices to cover all the edges of the graph G. Okay. See, let us find some other set here, I. Okay. If I take I, that would cover this edge, this edge. So I have to take an edge which covers HB. Suppose if I take H, okay, similarly I take F and G. Okay, I am trying to find a set which is larger than S1. Okay, but of course you require only the minimum. Now I am trying to give you a covering set which is minimal. Okay, which is minimal. That is, a proper subset is not a covering set. Okay, so I have taken I, H and then F, G. So when I take this F and G, it would cover the triangle, edges in the triangle EFG and B, H, I. So now I have to cover the edge AB, AE, BE, CD, BC and ED. So in that case, what I will do is, I will take this edge A, B and C. Okay. But when I take this B, I think H need not come. Okay. So what I will do is I will omit B. Okay. I will take A, that would cover, if I take A, that would cover A, B, A, E. Okay. And here I will take C. When I take C, it would cover C, D. Okay. And C, B. And now what I will do is I have to necessarily take, to cover this edge BE, I have to necessarily take any one of the vertex, either B or E. But when I take B or E, automatically I will have a subset. Say for example, if I take B here, okay, I have to omit this H. Okay, because I won't get a minimal covering. So I will omit H and I will take B. So now when I take I, these two edges are covered. When I take F, these two edges are covered. When I take G, this edge is covered. When I take A, these two edges is covered. When I take B, these three edges is covered. When I take C, this edge is covered. So, I have to add D, because when I take E then I will have a problem. So, what I will do is I will add E, that would cover this. So, this is again another covering set, which is also a minimal covering set, because when I remove any one vertex, this ceases to be a covering of a graph. Suppose if I remove I, the edge IH is not covered. Suppose if I remove F, FG is not covered. Suppose if I remove, okay, if I remove I is not covered, but suppose if I remove F, EF is not covered, sorry, EF is not covered. When I remove G, EG is not covered. When I remove A, AB and AE are not covered. When I remove B, okay, when I remove B, what will happen? BE is not covered, okay. And when I remove C, CD is not covered, and when I remove D, DE is not covered. So, this will be a minimal covering of a graph G. And here the minimum, okay, beta of G will be minimum of this. What is this? 1, 2, 3, 4, 5. Okay. Here I have 1, 2, 3, 4, 5, 6, 7, 7. Okay. But what I want is a minimum cardinality of a covering set is called as the covering number of a graph G. Okay. So, that is the concept of covering. So, as I told you, we have a theorem, what do you call it as, in a simple graph G, I am finding the relationship between independent set and the covering set. In a simple graph G, okay, S is an independent set if and only if V minus S is a covering set of G. Okay. Suppose if I have a graph G, it will be G. If S, if this is an independent set, then V minus S, this will be a covering set of G. This will be a covering set of G. So, we will look at the proof of this. Okay, what is the proof of this? What I will do is I will take, let S be an independent set. What is an independent set? Any two vertices in S are non-adjacent. So, that is the definition of the independent set. If I take any two vertices, that will not be adjacent. So, they are non-adjacent. So, what happens in a graph G, okay, any edge will be incident with a vertex in V minus S, be incident with a vertex in V minus S. So, obviously, you can see that if I have an edge here, it has to be incident with it. Suppose if I take any two vertices, it cannot be adjacent. If it is adjacent, then it violates the condition of the independent set. So, in this case, what happens here is that if you have any edge, that will be incident with a vertex in V minus S. So, if I take any edge, if it is incident to a vertex in V minus S, then automatically this gives you the definition of covering set. The set V minus S is a covering set of G, is a covering set of G. Okay. So, in this case, what happens here is that if you take an independent set, then its complement is a covering set. Okay. Now, for the converse, if you take conversely, let D be a covering set of G. Okay. If D is a covering set of G, what does it do? Any edge of G is incident with a vertex of D, is a incident with a vertex of D. So, automatically what does we do? The edges or we will put like this, okay. Any edge of G is incident with a vertex of D, okay, this will be better. Now what I have to do is, I have to show that V minus D is an independent set, okay. Let E be an edge of G incident with vertices in D, okay. Sorry, vertices in V minus D, not D, V minus D, okay. If it is incident with a vertex in V minus D, suppose we will have like this will be a covering set D, okay, this will be V minus D, and if I take any two vertices here, okay, an edge which has got two endpoints in D, okay, this violates the definition of D, or okay, when this violates the definition of D, or suppose if I have E is equal to UV, then either D union U or D union V will be a covering set of G, okay. So in this case what happens here is that it violates the definition of D, and therefore you cannot have, we cannot have an edge incident with vertices of D, incident with vertices of D, so vertices of V minus D. Therefore the set V minus D is independent. So the problem of finding an independent set is same as finding out the minimum covering, which is going to be the complement of the set. So in this case this theorem is important only because of it. What is the importance of this? Because in most of the cases we will be finding the independent set, and it is not that easy to find the independent set of a graph. So in that case what we do is we find the complement of an independent set, namely the covering set, which is little bit easier when compared with finding out the independent set, okay. And as a corollary to this theorem, you have a relationship here, okay, in a simple graph G, in a simple graph G, alpha of G plus beta of G is equal to n, where n is the number of vertices. You can get it from the theorem proof. Be very simple. Let S be a alpha of G set. Okay, what is an alpha of G set? The set S is an independent set with maximum cardinality. Independent set with maximum cardinality. So what is this independent set do? This is an independent set with maximum cardinality. If it is of maximum cardinality, we have proved that, and moreover it is also an independent set. So what we do is, by the theorem, okay, by the theorem V minus S is a covering set of G. V minus S is a covering set of G. Okay, but what is this beta of G? Beta of G is the minimum covering. So naturally any covering set has to have a value greater than the number of elements in a minimum covering or equal to the minimum covering. So in this case we have thus beta of G will be less than or equal to cardinality of V minus S, which is nothing but n minus alpha of G, or alpha of G plus beta of G is less than or equal to n. So this will be the first part A. Okay. So in this case if you take an independent set, okay, then its complement is going to be a covering set, and because of this we have the inequality alpha of G plus beta of G less than or equal to n. But here in the theorem I have to show that alpha of G plus beta of G is equal to n. So what we have to do is, okay, I have to prove the inequality alpha of G plus beta of G is greater than or equal to n. So to prove the inequality other way, I consider D a beta of G set. Okay, what is this beta of G set? The set D is a covering set with minimum cardinality. So that will be the result, minimum cardinality. Okay. And now when you take a covering set with minimum cardinality, okay, then by the theorem the set V minus D is an independent set, okay, and the set V minus D is independent set, so it has to be, okay, less than or equal to, alpha of G, because alpha of G is the independent set with the maximum cardinality. So in this case what happens here is that that is cardinality of V of D is less than or equal to alpha of G, and this will be n minus beta of G less than or equal to alpha of G, or alpha of G plus beta of G is greater than or equal to n. Okay, I call this as A and this as B. From A and B, okay, from A and B we get, what do we get? Alpha of G plus beta of G is equal to n. So from this you will have alpha of G plus beta of G is equal to n. So finding out alpha of G or finding out beta of G is same. Perhaps when you find alpha of G using this relation, you can find beta of G by subtracting it from the total number of vertices. So this will be the procedure, and if you find attacking a problem on independent set to be difficult, you can opt for a covering of a covering set of a graph. And if you feel that covering set is of difficulty, then you can go for the maximum independent set using this relation. So this is the main point that has to be thought of, because if you go through alpha of G, then the solution may be difficult, but when I take its complement it could be easily solvable. So keeping in this mind, we have this famous theorem which relates the covering number and independence number of a graph G. Okay, but of course as I told you, we will be interested in finding out the all independent set enumeration of maximal independent set. So that is the crux of this lecture, maximal independent set. Okay. but of course I am going to use the idea of Boolean arithmetic. Okay, and this you would have already studied, or it is easily known to you, because any computer, if you want to study any computer paper, you will have this digital calculations, Boolean algebra. A into A, or product of A and A is A, and similarly sum of the same element will also be A plus A is A, and then you have another result, A plus AB is equal to A, and the same result, A plus B into A is A. In fact, these two are same. I have written this for our convenience. When I use this, I will have AA plus, I can write this as BA, which is AB commutative, which will be A. AA is A plus AB is equal to A. Okay. So as I told you, these two are same, but for my convenience, I have taken these two. So we will be using these 4 important rules to simplify the Boolean expression. And based on the definition of the independent set, you have to convert the given problem in terms of a Boolean expression. And once when you are able to convert the set theoretical notation into a Boolean expression, then automatically you can enumerate all the maximal independent set. Okay. Let me again recall what is the definition of an independent set. S is an independent set if any two vertices in S are non-adjacent. They are non-adjacent. Okay. So in this case, suppose if I take an edge E is equal to UV, okay, is an edge, what will happen? Either U or V is in S. Okay. So now what I will do is, I will put this Boolean expression, set of all edges x, y in E. Okay. And I cannot have an edge, or I cannot have the endpoints of an edge to be in the set S. So naturally phi of 0 will be 0. Phi will be 0 always, because this should not happen. I cannot have both the endpoints of an edge to be in an independent set. So now what I do is, I take the complement phi dash, which will be f1 plus f2, say for example if I assume this f1 plus f2 plus so on fk, then automatically phi dash has to be 1, this has to be true. I cannot have both the endpoints in the set, so I will have either 1 in the set, and this has to be true. Phi dash should be 1 always. If phi dash is 1, then what happens here is that any one of the fi should be 1. So when I find this phi dash and remove the elements which are not in the expression of phi dash, then that will give you an independent set. So enumeration of all the independent set can be done using the Boolean expression. So in this case, I will take an example, okay, an easier example, and I will enumerate all the maximal independent set. So I will have like this A, B, C, D, E, F, G. Okay. So now as usual what I do is, I take the set of edges as a product AB, okay, plus BC plus BD plus BE plus CE, okay, plus E plus EF plus EG plus FG. Okay. So here I have totally 3 plus 3 6 plus 3 9, 1 2 3 4 5 6 7 8 9 edges. So phi is equal to the set of all edges which is given written here. So now when I calculate phi dash, that will be A dash plus B dash into B dash plus C dash into B dash plus D dash into B dash plus E dash into C dash plus E dash into D dash plus E dash. The next one would be E dash plus F dash into E dash plus G dash. The last one F dash plus G dash. So I have taken the complement. Now what I am going to do is I am going to simplify phi dash, and after simplification I can be in a position, or I will be in a position to enumerate all the maximal independent set. So now what I will do is I will first group the 2 by 2. Okay, I will group this 2 by 2, and then I will simplify, and then in total we will simplify the required expression. So when I do it, I will have A dash B dash plus B dash B dash plus A dash C dash plus B dash C dash. I have just multiplied the first two, and similarly when I multiply the next two, I will have B dash B dash plus D dash B dash plus B dash E dash plus D dash E dash. Okay. Now when I multiply the next group, C dash D dash plus C dash E dash plus E dash D dash plus E dash E dash, and then when I multiply the next two, I will have E dash E dash plus E dash G dash plus F dash E dash plus F dash G dash. The last one would be F dash plus G dash. Okay. Let me write here: AA is equal to A plus A is equal to A plus AB is equal to A plus B into A is equal to A. I will be using this 4 to simplify this. E dash into E dash will be E dash. Similarly, I will have E dash here, I will have B dash here, similarly I will have B dash here, and when I apply the third rule, A dash B dash plus B dash will be B dash, B dash plus B dash C dash plus A dash C dash. Okay. And I can replace these two with B dash. Okay, again using the third rule, and this will give you B dash. When I use this B dash plus D dash will be B dash, and then B dash with B dash E dash will again give you B dash plus D dash E dash. Similarly here E dash plus E dash D dash is E dash, then E dash with C dash E dash is E dash. So I will have E dash plus C dash D dash, and then similarly here I will have E dash plus F dash G dash. Okay, E dash plus E dash G dash is E dash plus F dash E dash is E dash, and that will give you E dash plus F dash G dash, and at the end I have this F dash plus G dash. Okay. So now I have to multiply these two. Again what I will do is I will multiply these two, and I will multiply the third and fourth. This will give you B dash into B dash will be B dash. This will be A dash C dash B dash. Now I will have B dash D dash E dash plus A dash C dash D dash E dash. This will be the product of the first two, and similarly the product of the next two I will have E dash plus C dash D dash E dash plus E dash F dash G dash plus F dash G dash C dash D dash into F dash plus G dash. Okay. So now when I use this E dash plus C dash E dash will give you E dash by root 3, and when I again use this with this, Okay, C dash plus E dash F dash G dash, this will again give you E dash. So this entire 3 terms can be replaced with E dash. So similarly is the case here, I can omit these two, because when I combine it with B dash C dash, I will have B dash. So I will have B dash plus A dash C dash D dash E dash, this will be the first term, and the second product will be E dash plus F dash G dash C dash D dash, and at the end I have F dash plus G dash. Okay. So from phi dash, which contains 9 terms, 1, 2, 3, 4, 5, 6, 7, 8, 9 terms, it got reduced to 3 terms. Let me again write this in the next slide. Phi dash will be B dash plus A dash C dash, okay, D dash E dash, D dash E dash into E dash plus, okay, what about F G C D, F dash G dash C dash D dash, okay, and what about the third one? Third one is F dash G dash, F dash plus G dash. Okay. So now what I will do is I will multiply these two, B dash E dash plus A dash C dash D dash, E dash into E dash will give you E dash, and now when I multiply this I will have F dash G dash C dash D dash B dash plus A dash C dash D dash E dash F dash G dash, okay, F dash G dash, C dash and D dash is already there, so I can omit C dash into C dash, will give you C dash, and similarly D dash into D dash will give you D dash. So now I have multiplied the first two terms, and I have F dash plus G dash at the end. Okay. Now again, can I think of any grouping here? Here if you see that you have this C dash D dash E dash, similarly you have C dash E dash E dash by the rule A dash C dash D dash E dash. So I have A dash, so A plus AB I can write it as A. So when I combine these two, okay, when I combine these two I will have A dash C dash D dash E dash, okay, and similarly I don't have BE, okay. So now what happens here, this becomes B dash E dash plus A dash C dash D dash E dash plus F dash G dash C dash D dash B dash, this is gone, and I will have F dash plus G dash. Okay, now I have to multiply these two. I will have B dash E dash F dash plus A dash C dash D dash E dash F dash. F dash dot F dash is F dash, F dash G dash C dash D dash B dash plus I will have B dash E dash G dash, and the next term would be A dash C dash D dash E dash G dash, and similarly this one will be F dash G dash C dash D dash B dash, G dash dot G dash will be same. Now if you look at this, these two are same, so A plus A is equal to A, okay, and similarly here I have, okay, let me write this, this will be B dash E dash F dash plus A dash C dash D dash E dash F dash plus, I have got twice, I will write it once, F dash G dash C dash D dash B dash, next one will be B dash E dash G dash, the last one will be A dash C dash D dash E dash G dash, okay. Now I have to check whether any of the terms can be still simplified, okay. B dash E dash G dash, I think this cannot be simplified any further. So your independent set, in fact maximal independent set will be, maximal independent set will be the elements which are not here, A, C, D, G. Okay. A, B is there, C, D, E, F, G. Okay. So here you have like this. And the second set would be A is there, B, C, D, E, F, G. Okay, this will be second set. And the third set will be A is not there, B, C is there, D, E, F, G. Okay. A, B, C, D, E, F and G. Okay. And here when I write for the fourth term, I have A, C, D, F. Okay. G is there. And when I take the last one, B, C, D, E, F is there. Okay. So you can see this. This is the we'll have like this. This is the maximal independent set for the given graph. This is the one that we have drawn here. A, B, C. This one will be D, E, F, and G. Okay. So now if you look at this A, C, D, F. Okay. All the four are independent. Similarly, you can check A, C, D, and G, that is also independent. So in this case, what happens here is that when you use the Boolean expression, you can enumerate all the all the maximal independent set. So now you can easily see that the value of alpha of G for this graph is 4. Okay, maximum number is 4. So this gives you the enumeration of the independent set using the Boolean expression. And to conclude, let me again recap what has been done in this lecture. Number 1, definition of independent set. Okay. The second one was definition of covering set. And the third important one is enumeration of maximal independent set using Boolean arithmetic. So these are the things that we had done in this lecture. We will continue with further topics in the next lecture. Thank you.